So I'll talk some miscellaneous topics, right? It's not a, like I will show you a slide where you can see you know, the basic things that you need to know, right? About LLMs. But some miscellaneous topic is what I will cover. Also use this time to ask any remaining doubts, right, you may have from the previous sessions. So I'll talk about scaling laws and various kind of LLMs. What are their main differences? Right? So where do they differ? So let's start. So when we talk about LLMs, they are language models. Right? They do language modeling, they do next token prediction. That's what they are doing. Now this started way back in 1948, where Shannon tried to model English language. And by the same logic, that how do you predict the next word given the previous 2 words, 3 words, you can predict. And that later gave rise to n-gram language models, that you can find the probability of the tth token given the previous tokens, and then you can use some Markov assumption. I'll use 1 token, 2 tokens, 3 tokens, right? So my model will predict probability of the next word given previous 3 tokens and so on. If I'm using a machine learning model, it started with RNN language models, transformer language models. I compute a loss that if I can't predict the correct word, I predict something else, I'll put minus log probability of the correct word. Minimize the loss, train my language model. That's where RNN language model, transformer language models were trained. And I mean, this trend continued. And so up to 2017, there was progress, little progress, but the main thing achieved in 2017 with transformers, right? Where now transformer combined with pre-training, yes, have given you very, very nice, exciting results in the field. And we saw about this yesterday that with GPT-3, you can just do things in context. That was even surprising. You don't need to fine tune. I can just do 0 shot, 1 shot, few shot experiments. Now, what changed? What changed, right? So one of the things that changed was the scale. In GPT-3, you're talking about 175 billion parameters. Now, no previous model had actually tried at such a scale. And at such a scale, people call it emerging behavior. Things started to emerge, right? Nobody thought about in-context learning is possible. And they found, yes, you can just put things in prompt and it will do the work, right? So, and then people started, thinking about it. That means I need to scale. It's more about scaling my model, huge. So when you scale, the question is, what can you do in terms of scaling? So what can you really scale? What can you really scale, right? So this was the paper from OpenAI, scaling laws for neural language models, right? Before that in NLP, when we used to teach, we talked about various empirical laws, like Gibbs law, Heaps law, very popular laws, right? And so now with neural language models, this was the first attempt for giving some sort of empirical laws, scaling laws. Like how do the performance scales with various parameters involved? Now the question is, then suppose you have to do this study, what would you do? So what are the kind of parameters? What would it depend on? So what do you think it will depend on? So first of all, if I have to study, how would I measure performance? So I have to do a study. So I'll say, okay, which language model is better? So I may have language model 1, language model 2. I want to say language model 2 is better than language model 1. How can I say that? What can be a quantitative measure for saying this? What is one single measure for saying this? Parameters. I give you more parameters without training the model, it's better. I'm saying, how would you say that this language model is better than another language model, right? Finally. Answered correctly, yes. But yeah, if you want to be even better, I mean, very correct in terms of the measure. Which metric and benchmark?
Blue metric, Roj
Blue
metric.
metric.
Super.
Anything else?
Roj.
Blue, Rouge,
Super glue.
super glue. Okay, so let me now talk about when you evaluate models, when you evaluate a language model, this is all called task performance, right? Task performance. It's also called extrinsic evaluation. You have trained a model, you are seeing how good it will do on a certain task. And you may do various benchmarks, super glue, and so on. Each has different accuracy metrics. Compute it, find out which one is better. But is there some intrinsic evaluation? Without going to the benchmarks, can I still find out what is the quality of my language model? Yes? This is a bit pre-deep learning thing, but you see any language model, they talk about this. And in your language model, they talk about this. How do you find out how good your language model is? What is a single metric for saying this? Perplexity. Yes, perplexity. So what is the perplexity? What is the perplexity of this language model? Now, what is perplexity? So what does language model actually do? It will predict the next token, right? So suppose you have a next tokens. I am seeing the scaling lodge. You predict one by one. I predict I predict M, I predict seeing the scaling lodge, and so on. You do one token at a time. So I can find what is the probability of predicting I given whatever I have previously, probability of M given, so probability of WT given W less than T. And I multiply over all the tokens in my sequence. I want this probability to be high for a good language model. And so what I do, I convert that into a form. So I'll say, okay, I'll take, suppose there are n tokens, so I'll compute some harmonic mean. If there are n tokens, okay, and that's what is perplexity. You take typically to compute it, you use log of this. So you take log of this, so it will be 1 by n summation log probability. That is your perplexity. What is the log probability for each token? You sum over all the tokens in your held out data. Okay, so L is the number of tokens, N is the number of tokens. Okay, so you compute perplexity. You can also call it loss if you don't use the negation. You can say if you use minus of this, minus of this, minus 1 by n, summation log. This is also called the loss. So you can either find out the loss. My language model should give me a lower loss. Should it give a, the loss should be low. And yeah. And without the log, should the perplexity be high or low? So yeah, actually what happens, you do a 1 by, right? This is the thing, you do 1 by this. Yeah, it's a positive value. 1 by this and to the power 1 by n. And that will become minus log. Also called the loss. So now, what is better, lower perplexity or higher perplexity? So your language model has a perplexity of 10 versus 20. What is better? So I want a lower perplexity. So I will prefer a lower perplexity. Okay. Because high probability, you are doing 1 by probability, so it should be lower value. It has some nice interpretation. For example, it tells you how perplexed you are. So the perplexity value is 10, it means when you are predicting the next token, you're as confused as if you have to make some random decision between 10 possible tokens. Okay. So there's some nice interpretation also. So you can compute perplexity values. And so this is how you will measure performance, right? Fine. Second is what will you measure against? So I'll say, okay, I'll find out the performance of language model using perplexity values, loss values. Now, what will you study against? What all it will depend on? When you're saying you are scaling, what can you scale? Yes? No, that is how you will evaluate. But when you develop a language model, when you train a language model, what all this scaling will depend on? How can you scale a language model when you're training it? Pre-training it. Parameters. So first thing is number of parameters. What else? Data set size, number of tokens or data set size. What else? Training time. Anything else? Huh? Sentence length, domains. Right. Yeah, there are many other things, but typically these are the main crucial things, okay, that you need to worry about. So typically depends on 3 factors. What is the model size? So how many parameters you have? So in the original paper by OpenAI, they did not include embedding parameters. They only studied other parameters. So how many parameters you have model size? Second is the data set size that you have. Third is the amount of compute. And how do you measure compute? So they gave some nice measure PF days. Anybody heard about PF days? Yes, PF days. What is that? So I've just given the definition. What is a petaflop day mean? So that means you're performing 10 to the power 15, that is a petaflop, that many floating point operations, right? Flop is floating point operations, petaflop per second. That's petaflop, doing 10 to the power 15 floating point operations per second. If you do that for a day, right? So it will be roughly 10 to the 20. You find out how many seconds are there in a day and multiply with this, right? So it will be slightly less than 10 to the 20. So you just multiply this by 60, 60, 24, roughly 8, 1, 4, 4, 6. How much is 764? 784. 764, 00. Or 864. 864. So roughly 10 to the 5. So that means you're doing 10 to the 20 floating point operations per day. So this is how they make some measure, right? How do they measure the compute? So then we will study how the performance scales with scaling each of these. What do you think? What will happen? If you scale any of this, you get more compute, you get more data, you get more parameters. What would happen with the performance? It should improve, right? So, but the only question is, will it improve linearly? Or what kind of graph am I expected to see, right? So again, what is the guess? Linear increase? No, with all of this, you keep other things fixed. Suppose you only increase your model size. Keep other things fixed, only increase your data set size. What will happen to the performance? It will improve exponentially, logarithmically, right? Log means makes more sense, right? So yeah, just to give an idea about the compute. So if you see in terms of 800 GPU has 312 teraflops, 3 times 10 to the 14 flops. So that means 2.7 times 10 to the 19 flops per day. So this is 1 PF day is equivalent to 3 A100s being used for the entire day. If you have 3 A100, you're using the entire day, that is 1 PF day. Okay. And yeah, so just to give an idea how many GPUs people use, like Llama model 2023 used 2048 800 GPUs. So 2000 GPUs. So that's the scale typically we talk about. They use 2800 GPUs for 21 days. Right? So you can say 2000 into 21, and that many into 3 would be the, divide by 3, right? That many PF days. Divide by 3. So that many PF days. And this actually costed them around $5 million, which is very small compared to what they have to do now. Same with GPT-3, it had V100 GPUs that time, 1 month of training, and okay. So now let's see how the performance improves, right? Changing the compute and all. So your loss is decreasing, and that's how you see that your performance is increasing. Yeah. And this is a log scale plot. So if you increase your compute from 10 to the minus 9 to 10 to the power 1 in PF stage, what happens? Data set from 10 to the 0 to 10 to the 9 and beyond, parameters, right? So what do you see? A nice linear relation, right, in log scale. So it's a power law that you're seeing. It's a power law. So that means, so they wrote the laws like this. So the loss in terms of the number of, so one is n is parameters, data set and compute. So n is what you actually have, n is a constant, alpha n is a constant, right? So it's inversely proportional, the loss, right? It will decrease if you increase the number of parameters. And the coefficient is 0.00076, here 0.095, 0.05. So typically when they give empirical laws, they give some equations and they say, okay, these constant will have roughly this value, right? Across, if you run this experiment across another data set, you may get slightly different value, but something similar will happen. So fine, nothing very surprising. So they're all following power law, and yeah, they're inversely proportional. Loss in terms of number of parameters is nc by n to the power alpha n. Nc and alpha are now constant. So you vary n, you see how your loss will change, and so on. They're different things. But then they said something else. They said, okay, this is good, fine. Now suppose, see, practical setting, what was the question? I have got 100 A100s, let's say. That will be the practical setting for 1 month. I'm able to rent some 100 A100s for 1 month. I want to train a model. So what should I do? So if my compute is fixed, what should I do? Should I focus more on data set or more on model size? It's a good question to ask. What should I scale, right? If I have a fixed budget of compute, otherwise, if you have infinite budget for everything, you keep on increasing, right? So that's what the laws say typically. But what if you have fixed budget? What would you do? So whether I'll focus more on the model side, data set size, both equally. So what do you think? How many of you feel I should focus more on the model size? I increase my model as large as possible. Not worry about data set much. In more focus on the model size. No one. One of you. How many feel I should focus more on the data set size? Okay, quite a few. How many of you feel we should focus on both equally? Model and data set. Equally. Okay, sure. Some of you. So nobody feels that we should focus more on the model size, right? We should think about more and more tokens, more data set. But our compute is fixed. So what did they find out? So findings. So I just put from the paper directly. So it depends strongly on scale, weakly on model shape. We saw that it depends on model parameters, data set, and the compute. 3 things. And there was nice power law, a smooth power launch, right? So across various orders of magnitude, you find nice power laws. Okay. But then they found something very, very interesting and surprising. They said large models are much more sample efficient than the small models. So they can reach the same performance with much fewer optimization steps and using fewer data points. So they found that it is more important to scale the model size. So if you have a large model, even if you show it less number of tokens, it will do well. Okay. So this is the plot that they showed. So you have a 10 to the power 3 parameters model and 10 to the 9 parameters model. Okay. So, and you see, this is the loss. So you fix a loss, let's say here. So even when this model is processing this many parameters, tokens, it is achieving the same performance as this model that is processing that many parameters, that many tokens. So even when you process less number of tokens, you can achieve the same performance by a large model. So that was something that came out from their experiments. So that means, fine, I can just scale my model and give it don't run it for many epochs. Nowadays, people don't even run pre-training for one epoch. You don't even run for one epoch because it's so much data, but you know what is important, the model size. Seeing sufficient data may not be seeing full data. It's okay. So, and then there are other things like optimal model size grows smoothly with the loss target. So you fix your loss target. So what is the optimal size that also? So for the same budget, it will be, so the yellow means more number of parameters. And you can even try to stop before you converge. So that is also fine. If you have like this much compute available, it's okay if this model stops early. That's fine. Other such plots, I mean, that was the most interesting plot. Then if again I use various parameter models and I increase the number of tokens in the data set, then the loss will decrease, it's fine. But you see, if you have very small number of parameters, it won't decrease much, right? And if you have a much larger model, so like this one, I can achieve even with processing very small number of tokens. Right? So scale more on the model size and then process less tokens. That's better. If you have more budget, fine, you keep on processing more tokens. But if you have less budget, you take a larger data set and train for less number of time, less number of tokens. And there's the number of steps they would need for reaching the loss function. And again, this is much smaller for larger models, number of steps that you need. Okay. And then they gave this nice picture, right? I mean, this is too much on the slide, so don't worry. So the same question that we were asking earlier. If you have fixed compute budget, right? And you can vary your N, model size, and data D. So D data size, they divide into two parts. So data size can be divided as batch size times steps. So this was the nice relation that they found. Compute is 6 times number of parameters, batch, and steps. And B times S is your D. So you divide your data into batches and then run it for many steps, right? So batch times number of steps is the data that you are using. And P is the number of parameters. So it's a nice relation. But the question is, if I have a fixed compute, how much should I focus on P versus D? Parameters versus data. So what they found from their experiments, so this D is roughly C to the power 0.27. Okay. And P is C to the power 0.73. So I should focus much more on the parameters than on the data. So they give an idea. Suppose you increase your compute from 10 to the minus 8 to 10. So in order of 1 billion, right? 10 to the 9, 1 billion. That much you have improved. So out of 1 billion, how much you will give to your model, how much to batch, how much to serial? This was typically, they said, you give 1 million to your model, 100 to your batch, and 10 to your steps. So increase your steps only by 10, batch size by 100, and model size by 1 million. Okay. So if you have more compute, I mean fixed compute, focus more on model size. If you increase compute, increase your model size more. That was the idea that they gave. Okay. Now, this was the initial paper on scaling loss, right? And it was interesting to know that I should focus more on model size. The only problem was that their experiments were still on the lower end, right? If you go back and see, I mean, they're talking about 708 million parameters, 1 billion parameters, right? But things have started going beyond, right? Things were like 175 billion, trillion. Chinchilla came with 1 trillion, 1 trillion parameters. Now, so then, yeah, this, I think I'll just show one more slide. So how did they do these computations and all for the experiments? So you may be able to relate to this. Okay, we did this in the class. So the underlying architecture is always a transformer. Okay, so how many parameters they have? So embedding is size of a vocabulary plus context window size times model dimension. Why? What are we counting here? What are we counting here? Embeddings plus also positional embeddings. That's where the context window comes into picture, right? How many words you can take in a sequence times the model dimension. That much is the positional embedding. So that is the embedding parameters. Then query key value and projection W naught, right? So query key value is each layer model dimensions times 3 times attention. D attention is the same as D model. So we got D attention times number of heads will give you model. So roughly 3D square times number of layers, projection D square times number of layers, feed forward, right? 2 times D model times D feed forward, number of layers. If you add all this and 2D attention edge, D model, and D feed forward edge 4 times D model, what would you get? DFF is 4 times D model, D attention is D model. What do you get? Same thing that we got. 4 plus 2, 6. 6D model into 2D model, 12D model square, right? Times number of layers. Remember, we got the same number of parameters for transformer. 12 times D model square times number of layers. And this is true for encoder only models and also true for which one? Encoder decoder or decoder only? Decoder only. It's not for true for encode decoder models, but true for decoder only models. Why decoder only models will not have this cross attention? There is no encoder. So what will they attend on, right? So decoder only models have the same number of parameters as the encoder only models. And this is valid for both of these. 12D square model times n layer. So if somebody asks you, oh, how many parameters GPT-3 has, how would you compute? You will ask, okay, what is the D model for GPT-3? And what is the number of layers for GPT-3? Anybody knows? It's 12 to 88, I guess. 12 to 88, just check. And this is, I think, 96. And just try this quick calculation. So do you get 175 billion? 175 billion parameters for GPT-3. Approximately. Yes? So this is a nice formula for computing number of parameters for a model. If you know the dimension of model and number of layers, and you know it's only a decoder only model or encoder only model, I'll do 12 D square model and layer. Okay. Multiply, you get the number of parameters. And this is what they did. I mean, now it allows you to even vary if your DFF is different, you can still compute. But typically, default, this is what people do. 12D square model into n layers. And then they computed what is the number of flops per token that they have to do. And this also is roughly double the number of parameters plus additional pass for the masking operation that you are doing. Only masking, you are doing number of context words. These are the additional calculation. So they just showed how they computed number of flops for different models. Okay. Now Chinchilla, when it came 2022, it said fine. There was already a scaling law paper. Now let's try it again with a larger scale. It's from DeepMind. Now, interestingly, they didn't find the previous things to be true anymore. So previous paper by Kaplan, and it said if you increase your compute budget, increase your model size more over data size. So if you have 100 times increase, model size is 25 times, data 4 times. Now what Hoffman said, from their experiment, they found out increase model and data at the same scale. Okay. If you're going for a large scale, then you increase both of them at the same rate. So if you have a 10 times compute increase, both model and data increase by 3.1 times, 100 times compute increase both model and data 10 times. Okay. So this is what they found at a much larger scale. Okay. Other difference was that they did not consider embedding parameters. So just recently, this paper came on arXiv, June 12th, 2024. They try to reconcile the two laws, the Kaplan law and Chinchilla law. And what they said is something interesting. They said, like for Kaplan, the optimal number of parameters was compute budget to the power 0.73. And Chinchilla said it's to the power 0.5, just a square root, right? Now, this can be attributed to Kaplan counting non-embedding parameters rather than total parameters. So if they try to put back the embedding parameters also in the Kaplan's study, they found it comes down to same coefficients. Because at Kaplan's scale, embedding parameters were quite significant compared to the non-embedding parameters. And they found, yeah, this actually holds fine. This is fine. So that means finally the current belief from this law is you increase your model and data set the same scale. Okay. So while Kaplan said something different, Chinchilla came back saying no, it's 0.5. Okay. Fine. So I talked briefly about scaling laws because this is crucial when you are trying to develop a pre-trained models, right? Now let's come back. Let's continue talking about LLMs further. So we saw that you heard about stochastic parrots yesterday. Anybody who does not know what is stochastic parrot name for? Why is the term? Yesterday you heard this term stochastic parrots. Yeah, I mean, you are just parroting your data. I mean, you have seen some data, you're trying to predict a token from one of the tokens that you have seen, right? So this is, as Professor Masan was saying yesterday, this is one of the view in the community, that extreme view, they're just stochastic parrots. But ChatGPT, after ChatGPT, I mean, people started to believe, no, there's more than that. There's more than that. There's another extreme view that, yeah, they have solved everything. Yeah. And there's also a view in between. Majority of people have a view in between. So, and what is different in the case of when you see this ChatGPT, what is different, right? Other than the language modeling objective, you try to predict the next token. What else is there in ChatGPT? If you see in terms of architecture, in terms of training paradigm, what is different in ChatGPT? So what are the steps when you train ChatGPT? So what are the steps? If I just ask for training a ChatGPT kind of model, what are the steps? Pre-training, okay, let's put it very simply, pre-train. take a model, pre-train your model, then instruction fine-tune. What kind of loss do you use in instruction fine-tuning? Again, same cross entropy loss. Cross entropy loss. Next word prediction. Pre-training, instruction fine-tuning, same loss. Cross entropy loss is typically what you use for training both of these. So till this point, you're only predicting the next word, not doing anything different. Okay. So what else is there in ChatGPT? RLHF. You actually take human feedback and do some RL, right? So now that RLHF has been covered yesterday, so let me ask some question. So do you take human feedback at runtime in RLHF, or where do you take human feedback? Why is the name RLHF? Where do you take human feedback in this algorithm? Does it happen at runtime? Training the reward model. So you take human feedback for training the reward model. And how do you train the reward model? What do you need explicitly? When you say you need human feedback, what do you need for training the reward model? Annotators? That's okay, but how will you take human feedback? What do you really need? Input, output, fine. And then what kind of feedback do you take? Preferences. So you have an input X and two outputs, let's say Y1, Y2. So it's a pair. And you ask humans which one they prefer, right? Which one do they prefer? Human preferences. Do they prefer Y1 or Y2? And you call them, one of them is losing sample, another is winning sample. Okay. So this is what you maximize in RLHF, the reward model minus a KL diversion term that ensures that your model does not depart too much from the base model. You are staying close to the base model, right? Okay. Now the two questions here, how do you implement reward model and how do you optimize reward? So what is the answer for the first one? How do you implement reward model? So you have this X, Y1, Y2. So how do you compute your reward model from this? So you have a prompt. See, in practice, what will happen? So you have a prompt. Based on the prompt, you have two outputs. And you go to humans, humans say, okay, I prefer Y1 than Y2. So how do you train your reward model? Yes? No, this is a paired thing. You know, Y1 is preferred than Y2. Then how do you use that to train a reward model? Yes. So you have to always start from something. You will start from pre-trained model. So even reward model will start from somewhere. So you train your reward model starting from pre-trained model, or you can even start from here, instruction fine-tuned model. You start from there, okay? And then we use this particular Bradley-Terry model. Right? So probability Y1 getting Y2 given the prompt is given by this score. And that's how you will put your reward model. So what will your reward model finally do when it is trained? So once you train it over a large data set of preferences, what will it finally give you? What can the reward model do finally? No. It won't give you most preferred answer. What will the reward model actually give you after it is trained? Yes? Rank? No. It gives a scalar value. See here, Rxy is a scalar value, right? So once your reward model is trained, then you give your reward model a prompt and a completion. It will give you a scalar value after it is trained. That's what you're training it for. You're training it to get a scalar value so that any prompt and an output, you can find the reward. What is the reward, right? A scalar value. So, and this is how you will train your reward model, right? This is the particular loss function that you use. Okay. And once you have trained your reward model, so you can get, given a prompt and output, you can get a scalar value. How do you use that in RLHF? How do you do RL with that? Yes. Yes. How exactly? So what will you do? So you have trained your reward model. Your reward model is trained. It's trained. And you have an instruction fine-tuned model. Now, how would you tune your final RLHF model? What would be the process? Yes, but I mean, in practice, what will you do? In practice, what will you do? Are you getting the question? So you have some data for pre-training, you pre-train your model. You have some data for instruction finding, you instruction finding your model. So you started from model 5 to 5.1, 5.2, right? And then 5.2, maybe you'll start from 5.2, you'll get 5.2 RM, reward model. This is 5.2, you can call pre-trained or instruction tuned. 5.2 IT, 5.2 RM. Initialized from 5.2 IT. You get 5.2 RM. Now, how do I get 5.2 RL or whatever, 5.3 RL? No. I mean, see, so here you also had some preference data that you collected offline. You trained your reward model using that, right? Pre-training, you needed pre-trained data, right? You needed pre-trained data. I needed some instruction fine-tuned data. So what will I need for going from this stage to an 5RL? What would I need? Do I need more data? Do I need more data? What do I need to train the RLHF model finally? But preference data we already used here. We already used preference data for training the reward model. So you are saying for going, so I'll initialize it from here, let's say. Okay. Now, what is the process? I'll take some X prompt. Let's say I have a lot of possible prompts, X. Fine, I'll take the X, then what will I do? I have a lot of prompts, I'll take X prompt, then that is fed to the No, you cannot fed just X to the reward model. You have to feed X with an output. Then reward model will tell you how good is this output for X. So which output will you feed to the reward model? So you are saying whatever output this phi RL is giving you, or whatever output this is giving you. So you're at some intermediate point in your training, you still call it phi RL. Let's say. So which output you will take? The given by the RL model that is currently being trained, or the instruction tuned model that is being trained, right? So I'll find out, I'll feed this prompt to the model that is being trained, and I'll generate the Y. So I'll get the Y that is given by the RL model that is being trained. Good. Then next, what I will do, I can now pass it to reward model and compute a reward. So I'll pass it to reward model and get a score. Reward for this sentence X. And once I get the reward, then it's a scalar value, reward is a scalar value. Then what would I do with this? Update the weights, right? And how do you update the weights? So anybody has that formula? What is the equation for that? Yeah. So I'll just write it here. So RS log interestingly, so they only used one sample. So although this Monte Carlo sample says that you have to take M samples and take an average, they only used one sample. Okay, so just take one sample. So this would be, if you just take one sample, that will be that sample that we have taken, X or S hat. You maximize this, that is minimize this. And this form is very similar to the normal cross entropy loss, except that it is weighted by the reward. What else is different? There's one more thing that is different. So here, this is a sample taken. It's not a ground truth. Just a sample, it's not the ground truth. In cross entropy loss, you need the ground truth. Here you have generated a sample, found out its probability, and you're continuing with that. So here asset is your Y. is not the ground truth for this prompt. So what you do in RL, you try to take a sample, you see what is the reward, and you update. So no, in approximating this, you are saying you are taking M samples. M samples taking an average. In practice, you just take one sample. You just take one sample. You don't take M different outputs for a prompt. Just an approximation, just a further approximation. Lot of simplification. So you can take M samples, you can also take one sample. So and in reinforced algorithm, you distribute it per token. So this will be exactly the same form that you are doing in your normal cross entropy loss, multiply by the reward, and you're doing it only for the sample. That's all, nothing else. So when you implement this, it's very similar to your cross entropy loss, just that you're not doing it for the ground truth, you're doing it for the sample, and you are multiplying by the reward. That's all happens. No, that's why I was asking what is the exact format. Just give me 1 second, I have it with me. It was actually exactly the same thing. Just 1 second. Yeah, this was the update rule that you were showing me. Yeah. So this was the update rule. And then it is fine, right? So the update rule was this. Just give me 1 minute, I'll just clarify this doubt. So this is the update rule. So theta t plus 1 is theta t plus alpha, that is learning rate, 1 by m summation 1 to m RSI fine theta t log p theta SI. Yeah. So this is the equation for weight update. So then it's the same thing. That's what I was saying. Yeah, this is already there, right? This is the update. So we are not taking further gradient. This is already there. So I'm saying just to understand this term, you can think about, yeah, just 1 more minute again. So you can write it like this. So this is phi t minus, so we know minus alpha, let's forget m because they take just one sample, alpha RSI delta theta minus log p theta SI. Right? So I'm saying we come back to the same form of cross entropy loss. So derivative of minus log p theta SI multiple learning rate plus this additional multiplication factor, the reward. Okay. And this you will again put it token wise. So when you will compute this loss, you have to compute token wise. So in terms of coding, nothing changes, only you have to multiply the reward for that sentence. And And you are doing it for a sample generated from your model, not from the ground truth. Generally, you always compute it for the ground truth sentence. Minus log probability to the ground truth. Here you do it, what we are generating. Okay, we'll come back after lunch, right? I'll continue from here. I'll talk about what are different kind of LLMs and what else can change. So one thing that changed was RLHF in ChatGPT. Before that, everything was using some next token prediction. So that's one thing, but what are the other differences that you will see?
While activating this large language model,
Mhm.
we also incorporate the general use of, let's say, early stopping, which is only fine-tune for, let's say, the year of the
No, you don't fine tune for that many epochs now. Even one epoch is not, you don't even do one epoch. Early stopping is very prevalent. You do early stopping. Yes. I don't do all the steps. I don't even go to one epoch. Yes. That's what is seen. You don't even need one epoch now. Many times people just do 1.5 epochs and they are fine. Yes. You have to have some held out data. No? You will compute your perplexity and loss on that. So, okay, I'll just summarize again RLHF pipeline, okay? And let me know if you have some major difficulty understanding. So, this is a nice way from Karapathi's slides to summarize what happens. So we do pre-training, right? Pre-training. Then we do supervised fine-tuning, okay? This is all fine. This is instruction fine-tuning, prompt response pairs, and you just do predict next token, language modeling. So first two phases are just language modeling. Now that's where the new things start, a reward model and RL. Reward model, what is the data that you need? Comparisons. I need prompt and I need at least two answers for the prompt. And human label saying that this is good, this is bad. One is better than other, sorry. Not good, bad, one is better than another. In low quality, so we don't need too many, but some comparison data. And from that, we learn the reward model, okay? And we showed what is the loss function. Now, I got a question. What is the format? What does reward model look like? Anybody has an answer? What does reward model look like? It's initialized from this model. Let's say the decoder only model. So decoder only model, you will feed the prompt and the response, and it is supposed to give you a scalar value. Now, how do you do that? It's a GPT model. How do you get just a single scalar from that? It will generate words. So how would you get a single scalar from that? No. So a reward model should do you what? A prompt response, give a score. That's why you need a reward model. To avoid human feedback at runtime when you run RL, I give a prompt, I generate a response from my model. I need to know how good is that response. So that's why I call, oh, reward model, tell me how good is this response. So you need a scalar. Prompt, output, what is the reward? Yes. So how does a GPT model, decoder-only model gives you just a reward, a scalar value? Yes. On where will you normalize? So something like this. So you will feed the prompt, completion, and have some readouts, a reward. At that point, you will apply some feed-forward layer, and that will give you a scalar value. Okay, that's typically how GPT was used for doing everything before. So you can just do regression, classification, whatever you want with a readout token. So you do some feed-forward on top of that, and you get a score. Just get a final score. So yeah, so you feed everything, and from that embeddings of the token, you predict is scalar, right? This is trained, this is trained. Now, once I have it, then in RL phase, what happens? Fine, I have prompt and completion. I just call the reward model. It will give me a reward. Prompt completion, give me a reward. Okay? And once I get a reward, I use it here to multiply and update my parameters. Okay, now tell me which part of this is not clear. Yes. No, see. Backpropagation means you're talking about training phase. In training phase, it always happens in a pair. So you have the same prompt, multiple responses. You know this is better than another. So you have the loss. We define the loss function, Bradley-Terry function. So you the loss, you come back propagate. It's a function of this token embeddings and then whatever else you're putting on top of that. RM training is not clear. Where? No. There is no, the ground truth is for the same prompt across multiple completions, which one is better? That's the ground truth that you have. So what will happen? Let's try. So what will actually happen? You have this reward model. So you feed the prompt response. You have this reward. At the final embedding, at the final layer embedding, single scalar from the embedding, and you do it for a pair. So prompt response 1, prompt response 2. So you have R1 and R2. And your loss is defined in terms of R1 and R2. So it was 1 by 1 plus e to the power something like R1 minus R2. And whatever else, you have the loss function, you backpropagate on that. This is all differentiable, defined in terms of the model parameters. For a pair. Yes.
In another pair for sample will come. Now it's a prompt 1 and response 3 or a new prompt and new response?
Are you talking about training phase? Training, you will only give pairs. So this is one pair that will give you R1 minus R2. So reward training is only via pairs. Prompt and at least 2 responses. At inference time, when you really need it, you will feed a prompt and response 1. Now this whole thing is there, you will just get the score. Look at the score. Is that clear? Any difficulties with this? Yes, previous slide. Yes. So we did reward model training. Now in RL, what is needed are just prompts. No ground truth data, only prompts. So with the prompt, you will pass the prompts to your model that you're training. You generate some output, get the reward, and backpropagate. There's no pair anymore. You take the prompt, sample a prompt, get the output from your model, get the reward, and update your parameters. That's all you're doing. RL training. Prompt completion, just the reward scalar value, and you increase the probability or decrease based on the reward. I mean, initialized from that. The model is initialized from that. Okay, but you're now training that. It's not frozen model. It's now under training. So you're updating the parameters of that model. You initialize from it, that's all. But now you're training this RL model. Okay?
The reward modeling is already trained.
Yes.
Okay, so as pre-training, then supervised fine tuning.
Then reward model training. Frozen. Yes. You're not training RM and RL together. Reward model is frozen. You just call it as a function call. So you just pass it and get the value. You're not updating the reward model with RL. Okay. So RM is trained before you do RL. Okay. Sure. Hope that is clear. Now, yesterday, one more thing was told. In RLHF, you need RL. People also tried to remove RL part while using human preferences. What was the method called? So if you want to avoid RL, if you want to do all this without using RL, what can you do? You want to still use human preferences without using RL. Yes? DPO, right? Yesterday, DPO was told. So what you do is use DPO, direct preference optimizations. Okay? So this is another very, very popular method right now that you don't want to do RL, fine, use DPO. What is the objective function? So you take a winning sample, losing sample. I was doing that in reward model, winning sample, losing sample. But what you are trying to maximize or minimize, so here you see theta and ref. Theta is the model you are training. Theta is the RL model. Ref is your pre-trained model. So you are seeing what is the score my ref model is giving to the winning sample. What is the score that my winning pre-trained model giving to the winning sample? You want it to be high. I want my ref model should give, or let me just quickly tell that there are two models. What was the ref model? Pre-trained one, instruction tuned model, reference model. Then I train from there to RL model, and theta is RL model. And remember, we said yesterday, I don't want the current model to diverge too much from the reference model, right? So here, what is the objective function? That I have a winning sample, I have a losing sample. I'll find out what is the probability given by my RL model to winning sample, probability given by my ref model to winning sample. Which one do you want to be higher? Should your ref model give a higher probability winning sample, or RL model give you high probability? RL. So you want this to be greater than 1. This should be greater than 1, ideally. Similarly, take the losing sample. So pi RL, YW, pi ref of PT, YL. Sample. Do you want it to be greater than 1 or less than 1? Less than 1? That your RL model should give it a lower probability than what ref model was giving. 1? Yes, that's what should happen. So that's where you define your loss. You say, okay, I'll actually write this minus this. If this value is less than 1 or less than 0, what should happen? If this thing in bracket is less than 0, what should happen? Is it an ideal case? Less than 0? No? So I should incur a loss. So if it is less than 0, what will happen? Sigmoid or something less than 0 is between 0 to 0.5. And I do a minus log of that. So I get a value above, value higher than log 2. Minus log, I'll get a value minus log x. X is less than 0.5, right? So this will be higher than log 2. If this value in the bracket is greater than 0, what will happen? My loss will be less than log 2. If the bracket is less than 0, and this is less than log 2, if the bracket is greater than 0. Do you think this is a good loss function? If the value is greater than 0, I am happy. My loss is smaller. If the value is less than 0, I'm not happy. My loss is higher. And the higher the difference, the loss will accordingly change. Are you following the loss function? So ideally, you want my RL model should give a higher probability to the winning sample than the ref model is giving. It should give a lower probability to the losing sample than the ref model is giving. I create a loss function out of that. This was DPO, no RL required. So you have preferences, prompt, losing sample, winning sample. Just compute gradient on that and update parameters, no RL. No reward model separately trained. So instead of training a reward model plus an random policy, you just have a single equation to update. Okay, that's how DPO saves. I mean, you don't have to train 2 different models. You just use this simple equation to update your parameters. And that's why DPO has become very, very popular in the last 1 year. Okay, so this was NeurIPS 23, I think best paper mention or something. And after that, this has become very popular, DPO, and many variants have come. So for example, GFIRE model, you might have heard about GFIRE model. This is fine-tuned from Mistral model. This is the first model that used DPO and actually was able to do very well in the evaluation test. So GFIRE was one model that used this. Similarly, Tulu2 that tried to even further took DPO to 70 billion parameters. And yeah, empty bench is one of the benchmark where it performed very well. And that's how the debate started, DPO or PPO. So RLHF uses PPO, and these models were using DPO, and many variants came. So right now in the literature, you will see there is KTO, there is SIMPO, there is, I think, CTO or something. There are many variants of DPO. Okay, but DPO remains very popular. And yeah, if you see really there, I mean, in the last 1 year, this has been a whole lot of models, right, that have come from different efforts, right? I mean, you might know few of these like Mistral, Y52, and we saw, yeah, right? I mean, Vicuna and others. So many different models. And this is like, yeah, a screenshot 2 months before. So this keeps on increasing. Okay. Now, how many of you can see this? Can't see this. Can't see this. Okay. So I just want to summarize the pipeline. Okay. Just to show what have you learned and what is still you will learn. Uh, okay. Okay, better, right? So how LLMs are built? So first step is getting the data, right? And you have to do a lot of data filtering and uh, noise removal. Once you have the data, next you have to build your tokenizer. In tokenizer, you know how to use byte pair encoding. There were other variants like word piece embedding and sentence piece encoding. I think Google gave them very early, but I think the byte pair encoding is the default method right now. Then you use a positional encoding. There are many variations. You can use absolute position embedding. Again, this can be sinusoidal, or you can train it. But if you see the recent models, they don't use this. They use something different, like relative positional embedding. So when you do query key matching, what's the relative distance between query and key tokens? Use that. So that is what is popular in relative positional embedding, rotary position embedding, relative positional bias. So these are various variations you will see. So why I'm showing, I'll show you some papers. They will say, I have used this particular method. So it's just a variation of what you have learned in the transformers, right? You learned a one way of positional embedding. People have found out this way is slightly better than what was used earlier. I'll show how this is done, rotary position embedding. I'll just show it in one of the slides. So positional embedding. So there are variations on how you do positional embeddings. Then what is the architecture? So we talked about encoder only, encoder decoder. And anyway, I mean, now everything is happening with decoder only architectures. Yeah, I mean, so you know all these, but right now it's only decoder only architectures in LLMs. Then how do you do pre-training? So typically mask language modeling and causal language modeling, next index prediction. Mixture of experts is just a simple variation in the architecture. I'll just briefly talk about that. What do we do in mixture of experts? You do model pre-training. In fine-tuning, you can do all this. Supervised fine-tuning, multi-turn instructions, instruction following. So whenever you have to build a chat model, rather than just doing an instruction finding, you have to do something called multi-turn instructions. So you have to have a dialogue kind of model for your fine-tuning. If you want to finally build a conversation agent. So you have to have multi-turn instructions. So that's why you will see Llama base, Llama chat. Llama chat will be fine-tuned on its chat data. Okay. So then you do alignment. Alignment previously used to be done by supervised learning, but now people use RLHF. And there are alternatives like DPO. I just briefly talked about DPO. There is KTO. KTO is even simpler than DPO, but I mean, same thing. You get alignment, your model is ready. Okay. When you deploy, you need to propose how would people decode from that. So that's why there comes a decoding strategy. So you can do greedy search, beam search, top K, top P. Okay. So these are the most prevalent right now. I mean, yeah. And yes. Tell me. We talked about it. In top K decoding, top K sampling, you will take your K is fixed. So K is 5, you will take top 5 tokens, distribute mass among them, and only one of these 5 will be predicted. In top P, what happens? You fix the probability distribution. So that means I'll take the tokens as long as they fill up 0.5 probability. As long as they become above 0.5, I stop. So it may happen that the first token has a probability 0.7. If my P is 0.5, I will not even go beyond first token. But if first token is 0.3, second is 0.1, third is 0.1, I'll take these 3 tokens and one of them will be generated. So it's the hyperparameter is different. One is I fix how many words. Second, I fix what probability distribution I will sample from. Top P. Is that clear? And then there are many things about how do you do cost-effective training and inference. Okay, so that's where how do you fine-tune these large models, right? So that's where this low-rank adaptation and other things, quantization and all these things come in. And this will be covered on 1st of July, right? There will be a session on 1st of July talking about PEFT methods, parameter efficient fine-tuning. That how do you fine-tune a very large model in a small collab notebook or, right? So what do you need? Because even to fine-tune a model like Llama 2, right? And you need huge resources. But if you use PEFT methods, you can still try PEFT with quantization. So you see, I mean, this whole thing, you have roughly seen most of the things. So like data, these are some typical data you use. The Llama paper gave this table. Common crawl is one data, 3.3 terabytes. C4, GitHub, Wikipedia, books, archive, Stack Exchange. There's some popular data that people use for pre-training. Already, I mean, some terabytes of data. Okay, I mean, people keep on working on creating more pre-training data. And then how do you typically try to categorize LLMs, right? This is one way. You can say in terms of parameters. Typically, if less than 1 billion parameters, a small LM, 1 to 10 billion, medium, large, very large. I mean, just some rough idea. That's how you typically characterize in terms of parameters. In terms of originality, I mean, are they the original models that are not fine-tuned? So this is a llama, or they are tuned models. They are like alpaca is based on llama. So you use llama, put some more data set, and train this model. Okay. Availability, are they public or private? Right? Like llama is publicly available, their weights are available, so it's a public model. And the weights are not publicly available, they'll become private models. So GPT-4 and all. And then what type of model is this? It's a foundational model that is only pre-trained, no instruction tuning, no chat fine tuning. Foundation model, instruction model. So also fine tune instruction following, or chat model. So typically people will write MPT7B, instruct, chat. Instruct means it's instruction fine-tuned. Chat means it's fine-tuned with chat data. Okay, so you will find with various models these names. Instruct model, chat model, and that's what it means. So how it is further fine-tuned after pre-train? What kind of data it is fine-tuned on? If it is not fine-tuned, you will simply find the name without instruct or chat. MPT7B, 7 billion models, model, no instruction tuning, no chat fine-tuning. Okay, and this anyway you can't see. So this is like some of the very popular models. their sizes and what kind of documents they are trained on. Like along the large models, Galactica, Galactia and this Falcon are popular, and then Flan is there. Among small size, Fire is actually quite good, and there are others here, I think. Gemini 9 billion and 27 billion have come up, right, just yesterday. And yeah. So yeah, whole lot models. They separate Llama family, Llama 1, Llama 2. Llama also, there's a code Llama and tiny Llama, 1.1 billion. And some models like Vicuna and Mistral, they started from Llama. Alpaca, Koala, they all started from Llama. And they further fine-tuned them, did RLHF and other things. Some did TPO. So for example, so once you know what all happens, if you are told this model, like Pythia. So know the creators, unique features, 8 model sizes from 17 million to 12 billion, and various checkpoints. Now, what is architecture? Transformer plus ROPE. What is ROPE? Rotatory positional embeddings. Plus swig loop. What is swig loop? You may not know, that's okay. If you know, you can tell. If you don't know, that's perfectly fine. So what is happening recently, all these models, they don't use the feed-forward layer agitage of the transformer. They use a variant of that. This is called swig loop. I'll just explain what is swig loop. Okay. It's just a variant of feed-forward layer, nothing else. And they say how much context they are using, 2000, and they're trained on 300 billion tokens. So this was the dataset, pile dataset. This has many, like Wikipedia, Stack Exchange, PubMed Central, and so on. 800 gigabytes of data it's trained on. Now, what is this ROPE and swig loop? Okay. So this is the rotatory positional embeddings. So what do they do there? The idea is, so you have the original embedding vectors. So what was happening till now in positional embeddings? You take the original embedding plus add some positional embeddings, right? Here you just multiply something. You do multiplication. Don't do addition, you do multiplication. How do you multiply? Multiplication should depend on the position. So that's why you have, if m is the position, you multiply by or rotated by m theta. That's all. So you take that vector, rotate by some theta in the vector space. And depending on the position, theta, 2 theta, 3 theta, depending on the position, you keep on rotating it. Okay. So, and you do it only for key and query. Values, you will keep it as it is. Only for key and query, you have to do the dot products. So it will also help in that it will take care of relative positional embeddings because you're rotating by the position. So it will take care of the relative position differences between query and key vectors. So this is the rotatory position embedding. You try to take the original embeddings and just rotate them depending on the positions. And the rotated things are being used for computing dot product between query and key. The values do not change. Values, the same idea. Once you get the tension, you take softmax and linear combination of the values. And there are actually quite a few variations, like absolute position embedding is what we have seen, but there's also relative position embedding, where it's a function of the position difference between query and key vectors. And this is what we have just saw in the previous slide, rotatory position embedding. There's also relative positional bias. This is addition. You have this dot product, you add a value that depends on the difference in the position, and then use that. Relative positional bias. So you have Q dot, you know this, these two Q3 and K2 are differing by -1, so you add something. So these two are additional, right? This is also additional, yeah, all these add something, and this does not add, this is just multiplication, okay? These two are actually quite similar. They both add something that is a function of the position difference between query and key values. Okay. Now what is SWIGLU? So you know ReLU, right? You know ReLU. This is the ReLU function. Now there are other functions like GLU and swish activation function. Now swish has this particular form. So it's swish of x is x times sigmoid of x. Also there is another parameter beta. Typically that is called kept as 1. So swish of x will be x times sigmoid of x. And this curve will look like this green curve. So it's a bit more differentiable function than ReLU. And this is, people find the swish function actually works better, the activation. So the one change that happens from FFN to SIGLU is ReLU gets changed to swish function. There's another change that is happening. You don't use the feed forward directly. So feed forward is this. Yes. X is the input. You multiply it with W1 and then multiply the output with W2. So X is the input, and you have a matrix W1. You get some output and another matrix W2. Right? In between, you can have some like ReLU function. So that's why you get max of X W1 0 and multiply with W2. Right? That is your feed forward. Now, what happens in SWIGLU is that they use gated linear unit, GLU. What is GLU function? So GLU is, you take the input X and take two different matrices, like W1, W2, you take W and V. Multiply X with W, also with V. Okay, so slightly different operation. So you get XW, XV, not showing the bias terms. And then you apply some nonlinearity here and do an element-wise multiplication with this. So it's a slightly different operation than feed forward. Parameters are roughly same, X, W, and V. Yes. Yeah. So you are still using, like you're using W1, W2, you're using W and V. But the operation is different. First you do XW, then you do XV. And then you do element-wise multiplication. Okay. So then there is GLU. You can do bilinear without using any nonlinearity. And SWIGLU, what it uses, here it uses swish function. So rather than using ReLU function, you use swish function. Swish activation, that was this. So this is SWIGLU function. So, I mean, it's a variation from FFN, and that people found to be working slightly better than FFN. This is SWIGLU. Are you getting some intuition of this? Yes. No, no, not like that. It's nothing like that. Yeah. Yeah, why people would use ReLU otherwise? I mean, then they won't use ReLU if that was the case. Yeah. No, no, no. They just found this is a slightly better function that works better empirically. Okay, so there's not a good explanation why do people use swish rather than really accept empirical results. Okay. So swish with beta edge 1 typically is used. So if you hear somewhere swiglu, that's what it is. So you use a separate activation function and you don't use feed forward, you use gated linear units. So take X, two different matrices, XW, XV, do element-wise multiplication. And to the first one, you apply a swish activation function. Okay. So many things have changed. So activation from rally to swish, and rather than doing feed forward, you do element-wise multiplication of two things. Okay. Now similarly, if you use Mistral and Mixtral, you will see that its architecture is transformer from rho P, same rotatory position embeddings, plus Swiglu. Now you know, okay, there's just a different way of doing feed-forward network, right? That's where the change happens. Plus it uses context of 4000, sliding window attention. Now what is sliding window attention? So in general transformers, a word attends to everything in the context. Yes, a word attends to all the word in the context. But that creates a limitation because the computation becomes very costly. So what people have tried is something slightly different so that models can use a large context. What is the idea? I'll show this sliding window first. So this is the normal attention. The cat sat on the whatever. So cat will attend on the cat, sat will attend on the cat sat, and so on. Yes. In sliding window attention, it will only attend on a window of previous k tokens. Okay, but doesn't that mean it cannot attend to the words that are far beyond in the window, right? So the idea that the argument that they give is this. Suppose this token can attend to all of these tokens, right? So the next layer, this token can attend to all of these tokens, and so on. So effectively, if you see across layers, the receptive field is window size times number of layers. So those of you who have read about CNS, they know about receptive fields, right? So if the window size is limited, that's okay. This word can attend to all of these words here, fine. And this word will attending all of these words, and this can attend to all of these words. So effectively, the length becomes window size times number of layers. So they make use of this observation, and they say, okay, we can restrict the window length. And if I had number of layers sufficiently large such that window length times number of layers is my context, I can effectively attend to all the words. Okay. I'll pause. Is that idea clear? I'm not attending to all the words at a go, but I'm attending to only a window, but I'm making use of the fact there are multiple layers. So if if this word can attend to here in one layer, this word was anyway attending to this word in another layer, and so on. So effectively, my receptive field is quite large. The window length times number of layers. So that's the idea that they use. Okay. So then I can use, yeah, because now you see, you will say, because earlier the complexity was the sequence length is square. That is the complexity of self-attention, but now it will become L times W. And W is smaller than L. You will only attend to W other words in the sequence, not all the L words, right? So that's how it will save. So this has been a very popular method, has been used across models. So there were actually many, many variations. I can't go through all of these. So just dense attention is what you have originally. It's dense attention, a word attending to everything. Then sliding window is like you're attending to only previous two tokens including, I mean, 3 tokens including itself. They also do some dilation like CNNs. So you can put some dilation here, right? Then people also tried this global local hybrid attention. Idea is that maybe a CLS token, everyone can attend to CLS token, or CLS can attend to everyone. So one token can attend to everything, but other tokens will only attend locally. So there will be some tokens, whenever there is a CLS in the sequence, it will be allowed to attend to everything else, and everything will be allowed to attend to this, right? But no. So it's a mixture of global and local attention. There's some tokens, global tokens are kept where everyone can attend to. And so on. I mean, there were many, many other variations. But you get the major idea. The only difference is, rather than using a dense attention, I use a sparse attention. And that is how I can, in the same computation time, I can attend to larger context. So that's why you have models that can increase context very, so they can use larger context by using the sliding window, global local attention, and other methods. Okay. And then we hear about this mixture of experts. So it is said that it's a mixture of experts architecture. Like, what is a mixture of experts architecture? Okay. This is again a variation from feed-forward layer. So in feed-forward layer, what you do, so typically what you do in feed-forward layer, so you have the input to feed-forward layer, and you have some force parameters. You multiply, and then you do something. A mixture of expert, what is done, you divide into multiple experts. So say these are 4 experts. You can call them as 4 experts. So parameters are divided into 4 experts. And then you have some attention mechanism of finding out what are the weights per token, what are the weights for individual experts. And then you find out, okay, I will only route one token to one expert, another token to another. So you find out which expert I should route this token to. So rather than using the entire feed-forward layer, the dense layer, what you do, you divide into multiple experts, find out which expert each token will be routed to. So that is a mixture of experts. So what is done? So suppose X is the input here. You have, say, WR, a matrix that is dimension of X times number of experts, right? And you get the logits. Then you compute the probability for each expert. From these logits, you apply softmax, come to the probability. Then what is done? You take some top K values from here and only route the token X to top K things. Now there are variations where you only route to only one, K is 1. So only one of the experts you will route this X to. So the PIX and EIX is the output of the expert on X. So if X is the input to the expert, what is the output it will produce? So there are variations where you can use multiple experts, or you will use only one of the expert. Okay, so this is the mixture of expert, a mixture of expert layer that is used in models. Yes. So that's what I said. No, rather than using a large 4 times D model layer, you use, say, 4 D model layers. Right here, this was feed-forward dimension was 4 times D model. So what you can do, you can use 4 different experts with D model dimension each, and then you route which one I will go. Each token can go to one of these. No, I mean, they're using it because this is better. This seems to perform better, mixture of experts. So this is the mixture of experts architecture. Okay, now, yes. No, it is being trained. No, it's the training time itself. This inside the transformer. It's inside the transformer. So, like you were training your feed-forward layer. Now you're just dividing into 4 different experts, and you're training them, right? So you will have W1, W2, W3, W4 for 4 different things, right? And you're training all these parameters in your training itself. It's not separately trained. It's not like you have trained experts separately and then you're brought in. No, you're training experts also. And you're also training how to give attention to the experts. So it's like just an additional attention is what you can say, right? So you're trying to put attention on these and see which one a token will go to. Like Olmo is another popular model created by AI, and you see its architecture, transformer plus ROPI, Swiglu. So you see most of the models now use this by default, ROPI plus Swiglu. Okay, and just context 4000 and so on. It uses some Dolma data set. This is 3 trillion tokens and common crawl, stack, C4, Reddit, stamp papers, books, encyclopedia, and so on. So, okay. Now, these are the main variations that you will see. When you read transform these LLMs, how do they vary from each other? They can use different position embeddings. They can use mixture of experts. They can use what else? Attention. They can use sparse attention, mixture of global sparse attention, and these variations. They can use different data sets. They can use instruction fine-tuning, chat fine-tuning. They can use RLHF, DPO, KTO. You see, you have all different type of plugs, right? So you can choose one way of creating a model and you have this. What data set you are using starting from that. Now, in one slide, I wanted to also show that while we covered this for text, this also is applicable for images, right? Like, you know how to encode text into a transformer. But how do you encode images into a transformer? So suppose you have an image. I want to use transformers. How would you encode an image into a transformer? What would you do? Yes? So transformer is a general device where you give a sequence, it will give you contextual embeddings and everything. I can give the sequence as the image package, right? So what happens in images? So when you use vision transformer, you take an original image and create patches and feed the patches as if they were different words, right? And then everything else is same. Inside the transformer, everything else is same, right? So then the only thing that you can learn, so suppose I create patches, how do I transform patches to embeddings? How do I transform an image patch to an embedding? I need some real vectors to feed to the transformer. And what will happen to position embeddings, right? Now this part is easy to answer. Position embedding is easy, right? So what you do is very simple. Suppose you have an image size H cross W cross C. Number of channels, C can be 3 typically when you take input RGB channels. So H cross W, let's say 784 times 784. So if you have 784 times 784 times 3 image, what you will do, you will create some N patches of some dimension P cross P. So what is N? So N will be H times W divided by P square. That many patches. I created patches, that becomes my sequence length. Okay. So N becomes my effective sequence length. Now, I need to have this mapping that how this P cross P patch of values between 0 to 255, or if you normalize 0 to 1, will go to an embedding scale, my model dimension. So for that, you learn an embedding matrix that is a projection that will take this P squared times C, because they have C channels, to D dimension, that is the model dimension. So you learn this embedding matrix of P square C times T. So in this case, suppose P is 16, 16 cross 16. So you will learn this 16 cross 16 cross 3. That is 768 times, if you want 768 of 512 dimension, 768 times 512 dimension. So that much embedding matrix you will have to train. So once you have trained this matrix, you take any 16 cross 16 patch, it can convert into an embedding. So you need to train this, plus you need to train the positional embeddings. Sequence leverage n plus the series token times model dimensionality. And that's all. This is the additional thing plus all the transformer parameters. And this is all is needed for training a vision transformer. So you define your P, create patches, and learn this embedding plus some trainable positional embeddings. And everything else is same. So there they use a CLS token because in images, they don't do pre-training. Typically, they didn't start doing pre-training like we do in language. They used to do on a large image in a data set where there was a class for each image. So that's why they had an image CLS token where you know what is the classification. So they use that during pre-training itself. So what is the class of this image? So that's where the loss is coming from. The loss comes from this classification. Okay. Okay, to summarize. So we talked about this whole pipeline, right? And as you can see, you know nearly all the modules involved in creating LLMs. Yes. And the base architecture is more or less finalized as of now. I mean, it's not the final, but at least as of now, seems like final architecture. There are various minor variations. For example, there are many techniques to handle long context. Okay. And then there are other things like positional embeddings, mixture of experts, and many, many things that happen. It's very easy for these architectures to extend to other modalities. They're very generic. They're not specific to text data only. So you can easily put in image data. You can multimodal. I want to put image, audio, video, everything, no problem. Create patches, create embeddings, and feed it to transformer. That's what people do. And pre-train them. Okay. So the idea of transformer pre-training is very generic to all the modalities. Details will surely vary, but idea is use the same architecture, but feed them into this embeddings. Now, what remains crucial though, although things have happened for English, general English, now what happens if I want to use it for low resource languages, domains where I don't have much data, like talk about finance domain, legal domain, health domain, right, where I don't have sufficient data, then data efficiency at various stages remains an important concern. Like these models have been pre-trained mostly on English data. They have very little exposure to many Indian languages and other data. Then what do we do for that? If we start from scratch, we may never have sufficient pre-training data that these models have. Or if we start from these models, then what should be the technique? So this remains still a very important concern. Other than, of course, the things that we have seen, like how do you extend them to core capabilities beyond like reasoning and right, that we have listened yesterday. So this also remains a very important concern. So, okay, with that, let me end this session. I don't know, this might look like a bit too much, right? But I don't want you to remember all this, right? Just to let you know that you see there are too many variations, but if you if you know the big picture, it's not so difficult, right? You know where the variations are happening. It's a small variation in feed-forward layer, position embedding, this, that. But you know the overall architecture. Sure. So, okay, any questions? So by the way, next session will be by Amrit. Has Amrit joined already?
Yeah, I'm here. I'm here.
Okay, hi. Amrit. So any
Hi.
questions? Yes. Okay. You know the CLS token from BERT, right? So it's the same idea. So in the transformer itself, vision transformer itself, they passed an additional token, CLS token. And what does that mean? It's something for which you have to learn what is the embedding. And then it will continue going through all the layers of transformers. At the final layer of transformer, you get some representation. Use that to find out the classification of the image, classify the image. That's what the loss will happen. So when you are training a model, you need to find out where is the training signal coming from. Yes. So in this vision transformer model, the signal came from the classification task. So you feed an image, you know the class. So the CLS token will help me in getting the final embedding. I'll then pass it through a classifier and then find out what the loss. I'll train my model like that. No, no. See, your data will be coming from a labeled data. The difference here was, like in language, you just take any corpus and predict next word. In image vision transfer, what they did, they took ImageNet data, where you have an image and a class. Okay, so you have an image and you also know the class. So you're using that as a training signal. I'm passing the image, I also know what is the class. So I predict the class and I compute my loss, backpropagate and train my parameters. It's only used for training the model. Okay. Yes. Which expert will get the token? Yes. It's just the attention. It's like attention. So which expert I should attend to or which expert I should go to? So they will learn which token, whether this expert is more likely to handle this token or this expert is more likely to handle this token. No, it's a difficult thing. I mean, you would have some classes, right? Maybe finally they will come up with, okay, so multilingual problems. So some expert is good at handling certain languages, some expert in another language. Maybe if it's only English, maybe it's more about domains, topics, right? So it can be anything because we're not giving any prior. So they're learning on while they're training, they're learning where to route one token, right? So no prior is being given. So it can be any part of the classification that they're learning. Yes, yes. No, that's what we are not deciding. Huh. Yes. No, it's the same thing as you were saying. How are you computing the query key attention, right? Originally, they all have the matrix. How do you know this word will have a more attention than another word? It's the same thing. Now you are putting attention on the experts and you are learning, are there some tokens that will route to some experts, another tokens to another experts? Yes. Essentially, the black box all in terms of equations, right? While training, some gets preferred and some don't. Size of each expert is same. That's how, otherwise you won't be able to combine the output. No? You are taking a combination of output. Each expert has the same size. But their representation will be different and everything else will be different. But their sizes are same. The formulation of EIX will be same. This function will be same. But their parameters will be different. You see, there's always a trade-off. I mean, can't keep on increasing. People have found 8 experts typically to be good, around that range, 8 experts. Okay. Many architectures you see 8 experts. Yes. New activation function. I think it's an interesting question. I don't know. I mean, many in the literature there are already some, right? And yeah, one can try out because there has to be some mathematical properties of the activation function, and then you see what empirically what works well. They were all old things. I mean, I don't think they were new things, the activation functions. It's just that they were applied to these architectures late. It's a hyperparameter. You can't train it with the model. It's a hyperparameter. So you fix it beforehand. Anything else? Okay, if not, thanks for listening patiently. I know this might have been a very heavy session, but I hope you got the main ideas. Okay. And so then I think let me stop sharing.